Hi guys, this is Nikhil Nehra, pursuing Bachelor of Technology in Engineering Physics from IIT Roorkee. As a part of my course based on the microprocessor and peripheral devices under Dr. Mang Goswami, I'm going to explain you the interfacing of 8085 microprocessor with analog to digital converter module. So before moving further, I will quickly explain about the whole kit. That one in the green color is an 8085 microprocessor kit, and whatever that you are seeing with the LEDs is that ADC module with the kit number 0809. The wires of that black and the red color is known as jumper, and that you are seeing of a silver color is an FRC cable. So as we look towards the observation and we are moving the knob from its extreme, so we can see that as we are controlling the supply for voltage from a 0 to 5 volt, and basis of that we are getting a data in a digital form on a LCD screen from 0 to FF. That means these are 256 values, and that's make a sense because it's a 8-bit microprocessor, so total possible values that it can shown should be a 2 to the power 8, and that's be a 256. So these are the some of the screenshots from my experiment, in which you can clearly see the actually I captured these screenshots based on the both the extremes. So in the first one, as you can see, the digital data is 00, means at present the voltage is 0. So that's the one extreme. And if you come to the other extreme, that the point when we are supplying the voltage at the 5 volt, we are getting our digital data to be FF, means 255 in a decimal, and all the LEDs are glowing. So now the question arises that how the digital data is varying with the rotation of the knob, means what in which function they are depending to each other. It can be an exponential, logarithmic, polynomial, linear, or the trigonometric. So next we look to these different possibilities, and finally we come to a particular conclusion. Now come to some insights. So this is a one table that I found based on my observation. So basically it contains three columns. So first one is an angle. So angle that I'm observing is not from this original position. It's a standard angle. Standard means that whatever the normal that you use, like a x-axis, y-axis, and whatever the default that we take in the standard notations. So this one is a 9. So these first that first column is the angle. Second one, the corresponding value that you observed, that in a definitely in a hexadecimal form, and after that in the next column I converted them in a decimal form. So means I want to tell that what the conclusion that you can draw from these values. So at 90 degree we are getting a value of 49, and 180 degree we are getting a value of 130. So means the difference is 81. So means we are getting a difference of 81 when we are changing the angle by a 90 degree. Okay, so and next we look to the second observation. At 135 degree we are getting a value to be a 90, and 225 we are getting a value of 171. So the difference is again 81, and again we are getting a difference of 81 when we are changing the angle by a 90 degree. And if you look even to the third and the fifth observation, the difference between them is near of 84. So means it's roughly to be same to be a 81 by 90, or that's if you change to the decimal form it's be a 0.91. Okay, so means that implies that that data that we are observing should be a linear function of the with the angle. Okay, so from our past table we came to the conclusion that digital data is a linear function of a voltage with a rate. It should be nearby of a 81 by 90, and that should be of a nearby of 0.91. So if we look to that graph, so I on the x-axis I plot about the degree of rotation, and on the y-axis I plotted about the value. So the point is that we came to know that it should be a linear function, and value are varying from its extreme from 0 0 to ff. And if you look to the degree of rotation as you do this experiment, it's not taking a full circle like a 360. So as you can even see that if 0.91 we are getting a change of a 0.91 per degree. So as for the 1 degree as a for a change of a one value, we should have a rotation of a 1 by 1 upon 0.91, and that's to be equal to the 1.091. Means to if I want to change the value to from a 1, means consecutive, I have to rotate the angle by a 1.09 degree. And if and similarly in that whole setup we have 256 values, and if you multiply 256 to a 1.09, we get that's 284.5. So now the question arises that how the conversion mechanism is working as a whole. So means how we are observing our discrete values as a function of a voltage. So it's based on a floor function. Actually the voltage is varying, we are actually varying the voltage from 0 to 5 in a linear manner, but the system is treating that in a discrete way. Like how this I'm going to explain through this that step function, that we are getting a value to be a 0 from 0 to 5 by 256 means actually we are getting a value, observing the value from we are observing a value from 0 0 to ff, that means 256 values. And and our voltage is varying from 0 to 5. So means for a 0 to 5 by 256 I'm getting my value to be a 0, and then from 5 by 256 to 10 by 256 I'm getting my value to be a 1, and in this same manner the whole pattern varies. Okay, so it's based on a floor function. So if I talk about my last slide, isn't that is a type of a ideal picture. But if you go to the lab and do this type of experiment, you will don't get a picture like that, and you will observe something that I shown in this video. So actually you will get a fluctuations, and even that guy, this guy is not changing the voltage, and means keeping the knob to be still at the particular angle. But you can see that the that last led is fluctuating, and if the led is fluctuating it means the value are fluctuating. So in the next slide we came to know that about what the reason behind that, and why these type of noises are occurring. Okay, so now come to the reason. Actually the reason is that means at the point when the value is changing from x to x plus 1, it's a range of a certain angle. Means that actually the system is not able to decide that either it will take x or at x plus 1. Means if you rotate a angle by even by a certain more extent, it will easily able to decide to be x or x plus 1. But in between, it's a in between a certain range of an angle, it's difficult for an instrument, for a whole system to be decided that it will take x or x plus 1. That's why in the last video we are getting a fluctuation at a particular angle. So now I come to the commercial and the industrial aspect of this ADC. So this type of an instrument are used in many of the purposes. So I just able to I just explain you some of the most common application of that. So first I will explain about the temperature sensor. So means how can you use this instrument to make a temperature sensor. So in this slide you can easily observe that even with the help of thermocouples, you can measure that how the whatever the change of the temperature that is that is going to take place in that particular experiment, we are getting in the form of a voltage change. And if you connect the voltage change with through the ADC interfacing module, it convert that whole data of an analog form into a digital form. So as a whole, what we are getting a result of a temperature change in a digital form, and that's known as a temperature sensor. So now come to next application of this ADC, that while recording audio or music clips. So actually, what is a while recording audio or music clips, you are simply recording the sound, and sound is a form of electromagnetic wave, and means if the wave that form of a analog. So and actually, while recording means you are storing that sound in a memory, means you are storing the analog uh, part to in a digital form. So that's the also a form of a that analog to digital conversion. Thank you guys. I hope that you have enjoyed this video, and please make a comment if you have any doubt, and just explore the beauty of microprocessor.